Welcome back to QHSE Talks. When we talk about ventilation in safety, most people picture air movement, fans, ducts, maybe comfort complaints. But that framing is dangerously incomplete. Ventilation is not a convenience system. It is not a background utility. It is one of the most powerful and most misunderstood engineering controls we have. Because here's the reality. Contaminants do not care about policies, procedures, or training. Vapors diffuse, dust migrates, gases accumulate, and unless we physically move air with intent, precision, and calculation, those contaminants will occupy the same space as the worker's lungs. That's why CSP Chapter 9 matters. This chapter forces us to stop thinking qualitatively and start thinking quantitatively. It demands that we answer uncomfortable questions. How fast is the air actually moving? Where is it moving from, and where is it going? Is it diluting a contaminant after exposure has already occurred? Or is it capturing that contaminant before it ever reaches the breathing zone? Ventilation, when designed correctly, does four critical things. It reduces contaminant concentration, it maintains oxygen balance, it removes nuisance and harmful odors, and it controls thermal stressors like heat and humidity. But when designed poorly, it does something far more dangerous. It creates the illusion of control. You can have air changes per hour on paper and still have overexposure in practice. You can have a running fan and still fail to capture a contaminant plume. You can even meet design intent and still fail workers if you misunderstand pressure losses, capture velocity, or distribution effectiveness. This is where safety professionals often stumble, not because the math is complex, but because the logic is skipped. General ventilation versus local exhaust, dilution versus capture, static pressure versus velocity pressure. These are not academic distinctions. On QHSE Talks, we focus on these decisions because they determine whether a contaminant is controlled at the source or allowed to migrate freely through the workspace. And once contaminants begin to accumulate, time becomes an enemy. Concentration builds, steady state is reached, and suddenly, exposure limits are no longer theoretical numbers in a table, they are thresholds that have been crossed. That is why CSP Chapter 9 is not about equipment, it is about accountability. If you approve a ventilation system, you are approving an exposure outcome. If you miscalculate airflow, you are miscalculating risk. And if you assume ventilation works without measurement, verification, and understanding, you are not managing hazards, you are hoping they behave.
And that's where physical engineering meets chemical risk assessment. It's that connection, as you point out, that is everything. Well, poor ventilation design, which, that just means poor calculation. It guarantees one thing. Chemical contaminants will accumulate. They will exceed the permissible exposure limit, the PEL, or the threshold limit value, the TLV.
So Chapter 9 is the toolkit.
It's the quantitative toolkit. It transforms a potential health hazard into a functional, reliable, and honestly, a life-saving system.
Okay, let's unpack this then. Before we get into the heavy lifting of the equations, we really need to establish the different, the philosophical strategies safety professionals use for moving air.
That's a great way to put it.
The source identifies three primary types of ventilation, and they seem to represent a pretty clear hierarchy of safety control.
Oh, absolutely. They're deployed based on the hazard level and the uniformity of the release. You wouldn't use a fire extinguisher for a paper basket on a major chemical spill, right?
Of course not.
And in the same way, you wouldn't use basic ventilation for a highly hazardous welding operation.
So let's start at the bottom. General ventilation, the lowest rung on this ladder.
General ventilation is the baseline. Think of it as simply moving air throughout a large enclosed area, relying on bulk airflow.
Like in a big office space or a warehouse.
Exactly. Places where potential sources of contamination are highly diffused and pretty much negligible. Maybe some trace emissions from a forklift exhaust or minor paint fumes in a huge bay. It's not for targeted control.
So it's more about temperature regulation or just general air mixing than it is a targeted safety control?
Precisely. It might slightly dilute the air, but it provides almost zero targeted contaminant removal. And this is the critical limitation the source really hammers home.
Which is?
General ventilation is absolutely not sufficient when you have specific high-hazard contaminants being generated or, when the generation rate is uneven. It's just too passive. It's too reliant on chance mixing.
Okay, which moves us up the hierarchy to the more focused strategy, dilution ventilation. This is where we start seeing the math really come into play, specifically to address the volume of contaminant.
Dilution ventilation is a much more deliberate strategy. The whole concept is to introduce a massive volume of fresh, clean air to mix with and, dilute the contaminated air.
Lowering the overall concentration of the hazard down to an acceptable level.
Hopefully below the PALO or TLV, yes.
I often think of it like thinning paint. You have a highly concentrated color, but you add enough clean solvent until the resulting mixture is safe to handle.
That's a perfect operational description. And the mathematics we're going to cover in part 3 today are the absolute core of this system. They answer that exact question. How much solvent, or air, do I need to add to my concentrated paint, the contaminant, to hit that safe level?
But it's not a perfect solution, is it?
No. Dilution ventilation is a double-edged sword, and the source is very clear about this. This approach is typically reserved for processes where the rate of contaminant generation is uniform and steady.
Okay, so a consistent process.
A consistent process, and crucially, where the substances themselves are of low to moderate toxicity.
So if you have an erratic spray process, something that sputters, or if the material you're using is highly toxic, say, something with a PL of just 1 part per million dilution is not a reliable strategy.
Not at all. The margin for error is just too thin. If the release is sporadic or sudden, dilution ventilation becomes pretty ineffective. You're just relying on random air currents to mix the contaminant before a worker can breathe it. It's a calculated risk.
Which is why safety professionals always prefer the third type.
The gold standard.
The gold standard, the precision tool of industrial hygiene, local exhaust ventilation, or LEV.
Yes. LEV is the definitive engineering control because it rejects that mixing philosophy entirely. It basically acts like a vacuum cleaner.
How so?
It captures a contaminant at its point of origin, the point of generation, before it can ever enter the general workspace air and threaten the worker.
And this is where the mathematical complexity in Chapter 9 finds its most robust and, let's be honest, its most demanding application.
Absolutely. And when a safety professional talks about LEV, they're talking about 4 components that have to work in perfect concert. If one component is miscalculated, the entire system fails to deliver the protection you need.
It's a chain, and it's only as strong as its weakest link.
Precisely. The system is a loop that starts with capture and ends with disposal.
So first, we have the hood.
The hood is the interface. It could be a simple duct opening, or it could be a specialized enclosure surrounding a grinder. Its job is to capture that contaminant plume efficiently.
And its design is critical.
Oh, critically. Its size and its design heavily influence how much airflow, or volume, which we call Q, is required to create the necessary capture velocity right there at the source.
Okay, component 2 is the duct.
The duct is the transport mechanism. It's the plumbing that carries the contaminated air from the hood to the outside or to the cleaning device.
And it's not just a simple pipe.
No. The length, the material which affects roughness, and the number of bends and fittings, they all introduce resistance. We call it friction loss, and it's a crucial element we have to calculate for fan selection.
Which brings us to number 3, and usually the most expensive component, the fan.
The fan is the workhorse. It provides the motive power necessary to overcome 2 things at the same time. First, the hood static pressure required to pull the air into the system at a high velocity.
And second,
all the resistance introduced by the ducts, the filters, the bends, everything. The fan is the physical embodiment of that flow rate, Q, calculation.
And finally, the 4th component is the cleaner or air cleaning device.
This is your filter, your cyclone, your scrubber, or whatever treatment unit you're using. Its purpose is to either remove the contaminant entirely, like capturing dust particles, or to treat gaseous contaminants before the air is exhausted back into the atmosphere or recycled.
So you're covering worker safety and environmental compliance.
Both. It's a complete system.
So Chapter 9 is essentially giving us the blueprint for quantifying the size and power of the fan needed to drive air through the duct at the speed required by the hood.
It's all connected. And that leads us perfectly into part 2, the core mechanics. It's one thing to define a duct, but to design it safely, we have to become fluid dynamics experts. We need to measure the invisible forces inside that tube, velocity and pressure.
Right. And this raises that really important question. How do safety professionals actually quantify this air movement inside a duct? I mean, how do we take an invisible flow and just assign a number to it?
It comes down to using specialized tools, primarily what's called a pitot tube, to measure the distinct types of pressure within the ductwork.
Okay.
Air flowing inside any enclosed system exhibits two forms of pressure that are critical in Chapter 9. There's static pressure, or SP, which is the potential energy pushing outward against the duct walls.
Like air in a balloon?
Sort of, yes. And then there's velocity pressure, or VP, which is the kinetic energy. So the pressure exerted by the air moving in one direction.
And it is that velocity pressure, the VP, that is the immediate key to calculating the speed, isn't it? It's the pressure equivalent of kinetic energy.
Exactly. Velocity pressure is the direct measurement used to calculate the airflow velocity, or V, within the duct. The foundational formula provided in the source material for relating these two is essential for every industrial hygienist. V equals 4,005 times the square root of VP.
Okay, so V equals 4,005 times the square root of VP. That 4,005 constant that's specific to standard air density conditions, right? Something like 70 degrees Fahrenheit at sea level.
That's right.
But here's where I have to push back a bit. If you're working in a hot, humid foundry or in a facility at high altitude in, say, Denver, doesn't relying on 4,005 introduce an immediate error? Isn't the calculation flawed before we even start?
That is the critical nuance that separates textbook theory from real-world engineering, and it's why these calculations demand such rigor. You're absolutely correct.
So it's not a universal constant?
No. The 4005 constant is derived from the conversion of standard pressure units to velocity units assuming standard air density. If the air density changes significantly due to high temperature, high humidity, or high altitude, that constant must be adjusted.
And if it's not?
If an engineer uses 4005 in an environment where the actual air density is, say, 10% lower, their calculated velocity will be too low, and the fan they specify will be undersized by 10%.
And that one small error means the required capture velocity at the hood face isn't met.
And the worker is exposed. That single constant, 4005, holds immense responsibility.
Wow.
It really does. But for most non-extreme environments, we rely on it as the starting point. Let's walk through the specific illustrative example from the source to see the direct calculation of airspeed.
Okay, so the scenario is, a safety professional takes a reading inside a duct and finds a velocity pressure reading of 0.2 inches of water gauge. That's H2O or WG. We need the airspeed in feet per minute, FPM.
Right, so we just plug that pressure reading into the velocity equation. V equals 4,005 times the square root of 0.2.
We take the square root of 0.2, which is about 0.447, and multiply that by the constant.
And the resulting velocity, V, is approximately 1802 FPM. The key takeaway here is how easily we convert a seemingly abstract measurement, a pressure reading in inches of water, into a tangible physical speed.
1,802 feet rushing past a point every single minute. This is the very first step in guaranteeing the system actually works.
Now that speed comes at a price. Air requires energy to accelerate and move, which brings us to the concept of understanding hood static pressure, or SP sub H. This is the crucial negative pressure the fan must generate to initiate that movement.
So the static pressure of the hood, the SPH, is what the fan has to overcome just to get the air from the room into the hood and up to speed.
Exactly. This pressure is composed of two primary elements: the velocity pressure, the VP, which is the energy required to accelerate the air, and the entry loss, or H sub E.
Entry loss, that's that resistance we were talking about earlier.
It's a bit more than just simple friction in the duct. Entry loss represents the loss of energy that occurs as the air changes direction and accelerates sharply from the huge static volume of the room into the small high-speed opening of the hood.
So it's turbulence.
It's turbulence. It's inefficient conversion of static energy into kinetic energy. It's the hidden drain on your fan's power.
So the relationship is SVH equals VP plus He. The total required static pressure is the sum of the energy needed for speed plus the energy lost to inefficient capture.
Exactly. And we could use the source's illustrative example to calculate this design parameter. Let's assume we have a hood design where we need a velocity pressure, VP, of 0.2 inches water gauge to achieve the required capture speed.
Okay.
And through design tables or calculation, the entry loss, He, for that specific hood geometry, is 0.1 inches water gauge.
So applying the formula is simple addition. SVH equals 0.2 plus 0.1.
The resulting hood static pressure, SVH, is 0.3 inches water gauge. This seemingly small number, 0.3 inches of water, is the non-negotiable requirement for the entire system design. The fan has to pull against this resistance to maintain the required velocity.
And as we move into part 4, we'll circle back to how important this entry loss coefficient is. The source makes a crucial note that in an actual LEV design, the calculation of airflow velocity has to specifically account for the coefficient of entry loss in the hood design.
That's the key distinction. We aren't just measuring the airspeed in the duct, we are calculating the airspeed at the point of capture, that crucial boundary between the hazard and the worker. If you ignore the entry loss coefficient, you will overestimate your capture velocity and contaminants will escape.
That level of precision is why Chapter 9 is the quantitative bedrock of industrial hygiene.
It is.
Okay, now we move into Part 3, the macro-level mathematics of control, dilution ventilation. If Part 2 gave us the tools to measure airspeed, Part 3 gives us the tools to calculate the exact volume of air needed to keep employees safe.
This is where we get into the weeds.
It is. This segment focuses on taking complex chemical properties and converting them into a required flow rate, Q, which is measured in cubic feet per minute.
These calculations are where safety professionals really have to integrate chemistry and calculus. We're dealing with rates of change, how fast a contaminant is generated versus how fast it's being removed. The final number, that Q, is the ventilation capacity we need to install to ensure concentrations never reach dangerous levels.
Let's tackle the first big calculation, calculating concentration buildup over time. This feels like a predictive tool, something used to analyze if an existing ventilation system can even handle a known contaminant generation rate.
It is. The underlying principle is modeling how quickly a concentration, let's call it C2, builds up after a certain amount of time, T has passed, given a continuous generation rate, G, and a fixed ventilation rate, Q. The equation is critical because it models nonlinear accumulation.
Right, the complexity comes from that exponential decay term, which represents the mixing process. Let's look at the explicit equation used to determine concentration buildup. It's C2 equals, in brackets, G over Q times the quantity 1 minus E to the power of negative Q times T over V, and then all of that is multiplied by 10 to the 6th.
That's it. And that last part, the times 10 to the 6th, that's just to convert the result into the standard reporting unit of parts per million, or ppm.
So that exponential term, the E to the negative Q times T over V, that's the crucial intellectual nugget here, isn't it?
It is. It represents the efficiency of the dilution process. If the ventilation rate, Q, is very low relative to the room volume, V, the exponent approaches 0, meaning the concentration climbs very quickly, almost linearly.
And why is that?
Because as the concentration climbs, the fresh air you're introducing is diluting air that is already contaminated. That's why the removal rate changes over time. It's not a straight line.
We don't need to walk through all the detailed arithmetic, but let's use the source's case study to really understand the implication of this equation. We are looking at acetone buildup.
Right. So the scenario gives us some very concrete inputs. First, the acetone generation rate, G, is 61.4 cubic feet per minute. That is a substantial release rate.
A lot of acetone.
A lot. The volume of the room, V, is 25,000 cubic feet. The time elapsed, T, is 60 minutes. And the current ventilation rate, Q, is 2,500 CFE.
So when a safety professional plugs all those numbers into that complex exponential formula, the source material dictates that after 60 minutes, the final concentration, C2, reaches 484.2 ppm.
And the insight here isn't the number itself, but the relationship. Acetone has a pretty high PL of 1,000 ppm.
So 484.2 is still below the legal limit.
It is, but the fact that the concentration has climbed to nearly half the limit in just 1 hour, despite having 2,500 cm of continuous airflow, reveals a crucial vulnerability in that system.
So what is that relying on this dilution system is a long-term liability?
Exactly. If the work shift is 8 hours, or if the generation rate increases just slightly, or if the ventilation system degrades because of filter loading, that concentration will very likely exceed the PEL.
So this calculation proves that you absolutely must run the numbers before trusting your general ventilation system to handle continuous volatile releases.
It shifts safety analysis from guesswork to prediction. That's the whole point of Chapter 9.
Absolutely. And that predictive power leads directly to the solution design in our next calculation. Calculating required dilution ventilation rate, Q.
Right.
If the last calculation basically said, you have a problem, this one answers, here's the volume of air needed to fix it.
This is probably the most fundamental calculation for designing a chemical control system. This specific formula is used when the contaminant is an evaporating liquid, and it directly calculates the minimum required volumetric flow rate, Q, that you need to keep the concentration of that chemical below the legal limit or the recommended limit.
This is where the molecular weight and specific gravity of the chemical become inseparable from the engineering design of the fan.
They're completely linked.
Okay, let's look at the structure of the equation because it's a powerful integrator of physical and chemical data. It's Q equals a big fraction. On top, it's 403 times 10 to the 6th times SG times G in pints per minute times K.
And on the bottom, in the denominator, you have MW times the PEL or TLV.
So the numerator holds the mass and the risk components. We've got the constant 403, which includes standard temperature and pressure factors, the 10 to the 6th for ppm conversion, the chemical's specific gravity, SG, its generation rate, G, and critically, the safety factor, K.
And then, as you said, the denominator is the physical tolerance for the substance, the chemical's molecular weight, MW, and the target concentration limit, PL/TLV.
Okay, that safety factor, K, that's where the rubber meets the road, administratively speaking.
Well,
What does K truly represent here?
K is the margin of error you build into your engineering control. It's an acknowledgement that the real world isn't a perfectly mixed box.
Yeah.
Air mixing is imperfect. Workers sometimes stand in unexpected paths of the contaminant plume, and environmental factors like open doors or temperature gradients create these localized buildups.
So if K equals 1, you are designing to the absolute bare minimum legal limit.
You are.
But if K equals 4, you're demanding 4 times the calculated airflow just to compensate for poor mixing or maybe a higher toxicity where you can't afford any margin for error.
Exactly. K is influenced by the toxicity of the substance, the efficiency of the room mixing, the location of the exhaust, the height of the contaminant release. For something highly toxic, K will be very high to guarantee worker protection. It's an administrative decision that's codified into an engineering formula.
And the source gives us a fantastic detailed case study using methyl ethyl ketone, or MEK, a really common solvent.
It does. So let's apply this formula to the MEK scenario. This is what the safety professional is given. First, MEK is evaporating at a rate of 1.2 pints every 60 minutes.
So that's a G of 0.02 pints per minute.
Correct. The legal limit, the PEL, is 200 ppm. Specific gravity, SG, is 0.81. Molecular weight, MW, is 72.11. And we assume a pretty strong safety factor, K of 4.
And that K equals 4, that reflects a serious concern about MEK's toxicity in the mixing environment, doesn't it? It shows the engineer wants a significant buffer.
A very significant buffer. So when all these inputs are processed, you're converting the volume of liquid using the specific gravity and molecular weight, factoring in the safety margin and dividing by the target limit. The source material yields a required ventilation rate of IntelliHill. Q is approximately 1810.7 centimeter.
And that is the crucial insight. A specific amount of liquid, 1.2 points an hour, and its chemical identity, MW 72.11, translate through this formula directly into a mandatory flow rate for the air system.
It does.
The result, 1810.7 centimeter, becomes a non-negotiable performance specification for the ventilation system you're going to purchase or design.
This calculation is the ultimate translator. It takes an abstract chemical risk and it converts it into a tangible, measurable requirement for mechanical engineering. If the fan you buy cannot deliver 1810.7 CFE into that system, the company is out of compliance and the workers are at risk.
That level of quantification is what makes Chapter 9 so powerful. Now, moving on to the third calculation, which is often overlooked but seems absolutely essential for emergency planning. Calculating purge rates.
This addresses that critical safety situation where the contaminant generation is stopped, the spill is contained, or the process has been shut down via lockout, tagout, LTO, but the air is still hot.
Meaning the room concentration is still above safe levels.
Right.
So we need to know how long exactly must the ventilation system run to scrub the room and reduce the concentration back down to a safe entry level.
This is a calculation of time and not volume, though the volume, Q, is a key input. The source notes that a specific equation, similar in structure to the buildup formula but solved for time, KT, is used here, and is under the assumption that the generation of new contaminants has stopped.
And the result of this calculation directly informs emergency response plans and administrative controls.
Absolutely.
Can you give us an example of how this plays out in the field? Why is the calculated purge time so non-negotiable?
Sure. Imagine a massive vapor release occurs, but the source is quickly isolated. The initial concentration might be, say, 1,000 ppm. The company wants the area to be safe for re-entry for maintenance workers at 50 ppm.
Okay.
The purge rate equation, factoring in the room size and the available fan power, Q, might calculate the required ventilation time to be 90 minutes.
So until 91 minutes have passed, or until air sampling confirms you've hit that 50 ppm target, the area remains closed. This calculation directly dictates administrative rules, warning signs, LOTO procedures.
Exactly. If the supervisor relies on a gut feeling and allows re-entry at 60 minutes, the workers are entering an area potentially still contaminated at 150 ppm. This formula removes the guesswork from critical emergency scenarios. It connects the physics of air exchange directly to worker safety protocols for re-entry and confined space operations.
And finally, Part D briefly mentions a general equation for calculating vapor or gaseous concentration.
Right. The function of this general equation is a bit broader. It might be used for predictive modeling or simulation or validation for highly toxic gaseous substances, where the whole concept of evaporation in pints per minute doesn't really apply cleanly.
So it allows professionals to confirm or predict the parts per million concentration of a gaseous substance against a known controlled release rate.
That's it. This would be crucial when you're dealing with things like toxic refrigerants or industrial process gases, where concentration levels have to be monitored almost continuously and with high fidelity.
It's a simulation tool.
It allows the safety engineer to perform what-if scenarios. What if the gas cylinder leaks at X rate? What concentration will we hit in Y minutes? It's a simulation tool based entirely on the physics of diffusion and the capacity of the ventilation system.
Okay, so Part 3 has given us the quantitative tools needed to manage a chemical hazard by predicting concentration buildup, determining the flow rate needed for continuous dilution, and calculating the time required for decontamination purging.
It's all about engineering risk out of the equation.
The math moves from theoretical air movement in a duct to real-world control of specific chemical threats like acetone and MEK.
That's right.
Now that we understand the volumetric and concentration mathematics, let's circle back to the structure that puts all this math into action. Local exhaust ventilation, LEV.
Right.
Part 4 is where we synthesize all these concepts. We need to see how the calculations from Part 2, the velocity and pressure, and Part 3, the flow rate, Q, dictate the actual design of the system components.
This synthesis is where the safety professional becomes an engineer. These four components, the hood, duct, fan, and cleaner, are not isolated pieces. They are interdependent variables in the larger system equation. An error in one variable creates failure in the final control.
Let's detail the function of each component again, but this time let's focus on the trade-offs that are dictated by the math in Chapter 9.
Okay. First, the hood. This component is defined by two numbers from Chapter 9, the target volumetric flow rate, Q, and the required capture velocity, V. The hood has to be physically shaped to convert the fan's static pull into high-speed air movement exactly where the contaminant is generated.
And a poor hood design means a high entry loss.
A high entry loss, which is inefficient and drives up the fan costs significantly.
Okay, the duct.
This is purely about resistance management. The required velocity, say 1800 FPM for certain dusts, has to be maintained through every length, every bend, and every piece of resistance introduced by the physical routing of the ductwork.
And if the duct is too long or has too many sharp turns?
The overall system resistance, the static pressure the fan must overcome, skyrockets.
Number 3, the fan.
This is the combination of all the math. The fan must be selected to operate at the specific intersection of two calculated values: the precise volumetric flow rate, Q, that you need, and the total system static pressure required to overcome the sum of all the losses.
The hood, the duct, the cleaner resistance, everything.
Everything. You cannot choose a fan based on Q alone. It has to meet that Q at the calculated system resistance pressure.
So if the engineer selects a fan that provides, say, 1810 cm, but only at 0.2 inches of water gauge pressure, and the system actually requires 0.3 inches, that fan will immediately run off its performance curve.
And it will deliver a lower inadequate flow rate in the real world. That is the cascade of error we have to avoid. The difference between 0.2 and 0.3 might seem small, but it could mean the difference between compliance and a completely failed system.
And finally, the cleaner air cleaning device.
While the math defines the volume, Q, the chemical identity defines the cleaner. The MEK molecular weight calculation determines the necessary flow rate, but the toxicity and physical state of MEK determine whether you need a carbon absorption system or just a simple dust collector.
So the math ensures the volume is handled, but the chemistry ensures the air is safely treated.
Precisely. The practical safety application here hinges entirely on interdependence. Every calculation in Chapter 9 is linked. An error in estimating the entry loss, He in Part 2, for example,
Leads to an inaccurate total system pressure calculation.
which mandates the purchase of the wrong fan. The fan then fails to deliver the required flow rate, Q, that we calculated in Part 3.
And the whole LEV system immediately fails to meet the PLL or TLV standards.
It's a chain reaction. The small nuance, the source details, using the calculation that accounts for the coefficient of entry loss when determining airflow velocity, is a final reminder that in precision engineering controls, we can't ignore mechanical losses, that turbulent friction is real energy loss, and that energy has to be accounted for by the fan to guarantee the health of the worker.
So safety isn't determined by a simple purchase order.
Not at all. It's determined by whether the calculated 1810.7 centimeter fan power is physically delivering the air velocity required at the hood face, overcoming all that calculated resistance.
That brings us to the conclusion of our deep dive into the complex mathematics of industrial ventilation found in Chapter 9. We've taken abstract concepts of fluid dynamics and concrete chemical properties and merged them into a quantitative blueprint for safety.
I think we covered 3 essential quantitative areas for the safety professional. First, mastering the physical measurement of air movement velocity and pressure using that foundational relationship, V, 4,005 times the square root of EP.
And ensuring that resistance, particularly entry loss, is properly factored into the hood static pressure.
Second, we detailed the process of calculating the precise volume of fresh air, Q, needed to handle specific chemical threats like acetone and MEK using complex formulas that integrate specific chemical properties.
Specific gravity, molecular weight.
With the required margin of safety, that K factor. And third, we synthesized all of this by showing how the physical design of local exhaust ventilation systems, the sizing of the fan and the dimensions of the hood are dictated entirely by those calculated flow rates and pressure requirements.
The math is the blueprint for the physical shield the worker relies on.
It is.
The source material shows us that air movement in industrial safety is not just physics. It's a carefully balanced chemical equation where every single variable matters. The next time you walk into a manufacturing facility, consider the complexity. The safety of every worker may depend on whether a formula derived from the properties of MEK accurately matches the power of the fan moving the air.
And remember that 4005 constant we talked about, the one relying on standard air density. While the formulas provide the perfect starting point, the operating environment is rarely perfect. What small, seemingly minor changes in real-world environmental conditions, a 10-degree spike in temperature, an unexpected surge in local barometric pressure, or a seasonal change in humidity, might subtly change the density of the air being moved.
Right, so if the entire system was calculated perfectly for 70 degrees Fahrenheit, those thermodynamic factors might subtly increase the air volume required, or they might reduce the fan's effectiveness.
Potentially reducing that calculated 1810 CF-meter down to, say, 1700 CF-meter.
And that tiny discrepancy caused by non-standard air could be just enough to push the worker over the permissible exposure limit.
That sensitivity to environmental change is why the quantitative foundation provided in Chapter 9 has to be continuously monitored and validated in the real world. It reminds us that safety is a constant calculation, not a static number.
We hope you walk away well-informed and with a new appreciation for the mathematics of clean air. Thank you for joining us for this deep dive into the quantitative core of industrial safety.
It was our pleasure.